in British Columbia in order to get off of carbon-based fuels. So he's offered, with the interaction, he's offered that if you disagree with some of his assumptions, you're asked to speak up, and we can try your assumptions and see how those assumptions change the projections, the calculations. So, Gil,
all right. Yes,
over
thank you.
to you.
Yes, thank you very much. So, this started for me, like I said, around 2010. I was home, I was sick with the flu, and then you start feeling better towards the end. And then, but you're not well enough to go to work yet. But you got you got a couple hours where you're energetic, and before you feel like crashing again. So I go, I'm curious about this. This is how big. If we were to try and get rid of all fossil fuels, let's just stop now. Life didn't change, right? Just how much electricity do we need to generate to replace fossil fuels without any other changes, right? No, that's not realistic, but it's a good. It was a nice little mental exercise. So so I came up with some numbers. Oop, we're losing our screen here. So I came up with some numbers. So then, and it was very interesting. And I won't say what they are because we'll get to the conclusions later when we see what my numbers are now. And then I offered Doug, says, if you ever need a pinch, I can put this together in a presentation and I'll update it to current numbers and current data I've been able to find. And we'll just relook at what this looks like. So what I'm looking to do, which one was it again? If we're changing the page, arrow. So what I'm looking to do is I'm looking at how much generators, right, that are we going to need, like a generator. So not, I'm always talking about energy and then going on. Well, we need how many? Oh, I think we need a few hundred gigawatt hours, and we'll be there, but as an engineer, there's something called energy, which is a joule, or in another form is called a watt hour, right? So, and then power for an engineer is the rate of doing work. So that is like a horsepower or a megawatt, right? So it's the ability of the machine to do work. It's not necessarily the energy output of the machine. But like I said, one of my pet peeves is everyone confuses power with kilowatt hours and megawatts or horsepower. So from keeping forward going on, we're going to stick with the idea that if I'm saying power, I'm talking the energy, the horsepower equivalent in megawatts of a generator. And if I'm talking, if I talk about kilowatt hours, I mean the energy, right? So that's what's going on with that one. So that basically it's just looking at how much energy we produce, right? So then I go from initial assumptions. So then the initial assumptions are, I said biofuels are deemed also to be green, so I'm not looking to replace them with generators, right? That's my first assumption. And then the values that I'm getting as an average day equivalent. So basically what I said is if you're looking, so if gasoline, the energy equivalent of gasoline is X number of terawatt hours, well, then I assumed, and I said that's over a year. And then I assumed, so every day, I just made an average per day, right? So I'm not looking at correction factors for fuel, like for transportation fuel, where your summer driving is a lot more than your winter driving. And conversely, your natural gas, where your winter heating is a lot more than your summer cooling with gas uses. I said, you know what, this is all going to balance out because I'm really doing a high level first cut at it. I'm not really going at the end detail. So the other thing I look at is I've broken it down. Is I got residential usage, commercial usage, industrial, and transportation. So and then basically is and that's how the energy I found was broken down into those categories. So residential is pretty obvious. Commercial those are things like your restaurants, your stores, your office buildings, that sort of stuff. Industrial is your industrial base, so large scale construction, your mills, mines, and all that sort of stuff. Factories. And then transportation, the obvious one, which most people talk about, is everyone only ever seems to talk about. That's obviously moving your butt from A to B in a vehicle, right? So you get in a car, or a truck, right? And also this includes transport for commercial. It's commercial transport, so the trucking and that sort of side of thing. That doesn't fall into the commercial side. It falls into the transportation side. So if it's on the road, moving from A to B, falls into transportation. So then the other one is just a little bit engineering speak now. So the energy consumed is based on end use demand, which is really the energy used by the end user. Because there's different ways of looking at it. One way is looking at it as the primary energy demand. That is a total amount of energy used in the process. And I didn't go there because a lot of that process energy just disappears when you transfer over. So for instance, you look at an oil refinery. An oil refinery is producing products. Some of the products are actually then being burned in the process to make other products, right? So if you would calculate that, if you're doing a carbon emission, you would use your primary energy demand, but we're looking to just generate. So I'm looking at the net output in the end. So that's why it's shifted over to end use. And really the difference is about 3 to 4% difference in the energy consumption, really, if you think about it. So based on the data I've seen. And then, and I'm assuming no population growth because some of the assumptions I'm doing are rounding out so much is BC Hydro did this years ago, or I said, I came up with a number for gasoline equivalent. BC Hydro came up with another number. And then their numbers was just like 400 megawatts different than mine. And the basic thing is they started assuming a lot of efficiencies in the usage of electricity. So that some of the existing usage of power generation was being transferred to these other uses as opposed to being steady state. I'm not going there with all this initially right now because most of that transition is, most people have already moved on to LED lights and stuff like that. So those are my basic assumptions. So out of curiosity, so we said, oh, well, then how much energy are we actually using in this province? So in BC. So I kept it for the engineers. I kept it in picojoules. And then I also converted it to terawatt hours. So, and if anyone wants to do the math, 1 terawatt hour is equal to 3.6 picojoules. So if you want to understand, so if you go to the metric system, I should probably wrote it down. So pica is 10 to the, where did I put it here? Petajoules, not pica. What am I talking about? So anyways, so peta is 10 to the 16. Tera is 10 to the 12. Giga is 10 to the 9. Mega is 10 to the 6. And kilo is 10 to the 3 or thousands, right? So just keep that in mind because that's the scale we're looking at, right? So how many zeros are on the end? I'm not putting all. Tera is 12. 12 zeros. So you kind of see, so I picked numbers through the years so you can see that. So total use of energy through the years, 05, 10, 20, 15, 20, are all, they're in a similar ballpark. And if you're looking at terawatt hours, they're all in the similar ballpark range, right? This total energy use hasn't really changed in 20 years. So you carry on. So what I've done is 2023 being the last year where the data has been updated to actually use as opposed to forecasted, because the data I'm getting it from was the Canadian Energy Regulator. So they have this one table that, or you can break it in different ways, but it would be giving me this energy. So I'm using 2023 now as the go forward value. So here are my starting values right here, right? So the keen one, if you notice, is electricity at 64.3 terawatt hours, right? For the whole year. So, and 11.2 of that was imported in 2023. Just keep that in mind. So, but I didn't factor that kind of difference in because I'll talk to the board in a minute. So that's the energy use. Anybody, that's the big picture, right? So then I'm coming down to, let's break it down. So let's go into, so start with residential, right? So here are my assumptions. The bulk of the fuel consumed is mainly not heating for the house, water heating and cooking, right? So in most of that case is it's mostly natural gas, really, in the end, really, for most people, right? Because if you're on heat pumps already, you're already into that electrical number, right? So you're not into this gas number. So, and then the electrification, what I'm doing is I'm assuming then that, okay, I'm going to take all this fossil fuels based on some efficiency assumptions that you get a net usage of this much energy is required, and therefore that results to this many generators. However, with residential, because it's mostly heating and cooking, you got, I'm assuming that where heating is going to be transferred to things like heat pumps. Cooking is going to induction stoves and ovens are small volume, small total of energy. And so the like heat pumps is the COP, is coefficient of production of 2 to 5. Heat pumps or induction heating is around 2 to 3 relative to gas, right? And it basically has to do is when you've got a pot on gas, a lot of heat goes around it, but induction just heats the pot itself. You pick the pot off, everything stops where gas keeps burning, right? So you get that. So based on that, so based on those assumptions, what we get is we get this. So if we had natural gas is 100 net usage, this is raw usage, this is the total energy of the gas, not after converted and everything, or so you got natural gas at 105 terawatt hours. You've got RPP stands for refined petroleum products. So that's anything that's coming out of a refinery. And they also include that liquid propane because it comes out of a gas plant. So gas plant for them is deemed to be a refinery. So all this is all the refined fossil fuel products. Biofuels and energy, hydrogen and other. And I'm making, for most cases, I'm realizing other is, for residential, other is, there is really nothing there anyways, right? So there was 2023, there was very little, not worth really mentioning. So that's what it looks like. So after you factor in your efficiency, so what I'm saying is the thermal efficiency of the fuel being burned, consumed is 80%. So what I'm stating here is that most furnaces today, not the high efficiency ones, are in the 75, 80% range. And the other thing, and I'm trying to keep everything on the low side as opposed to make everything really high. So therefore, at 80%, and then like I said, the electrical beneficiary, the efficiency of going to a heat pump and induction stoves and all that sort of stuff is a factor of 2.5. So when you put this together, so you end up looking at this, is that I have a net usage. You need to add 740 megawatts of generator capacity in this province just to meet your residential needs. So that's where I'm at now. So the interface, so now I can just switch over to the spreadsheet somehow. You didn't load the spreadsheet? Oh. So because that's my interaction portion of it. So one of the interesting things is that you can see it, like I said, the main usage is natural gas. Because you look at the size of it, natural gas is like the dominant thing for home usage, right? If you're not already on electric heat of some sort. So. Here we go. You showing it? Oh, no. Nope, not liking it. Anyways. Nope, no luck. Anyways, here. Let me get mine going here. So. So if you want to challenge it, we're there now? Oh, there we go. So switch it over to. So we'll click on residential. So here we go. So here's, oh, let's not switch to that page. Let's switch over to that page. There we go. Okay, there you go. So like I said, so there it goes, 2023 numbers. And then this is just spreading the use, showing the spread of the power range. So if you can see, like, electricity is 46% of the, and natural gas 45% of the total energy of used in your home in a year, right? So on average for the average home dwelling. So then, so that works out to 20 terawatt hours per year. And then I assume 80% to factor in a year. And then I go into terawatt hours. So then you come along and you got, so there's your terawatt new. So therefore there's your new, this is your net usage. So this is the net amount of energy that did work, right? So if you factor out the efficiency, so this is the amount of energy it started with. This is how much energy you actually use to do something, as opposed to the rest of it is waste, right? So then I said, all right, and then you want to apply your correction factor. So then this becomes the new value per year, and then you go per day, and the result of that is 700. Because once I reduce it to an hourly rate, megawatt hours per hour, that is literally a direct transition into the power of a generator. So if you follow my math a bit there, so as the engineers say, is always follow your whatever the component that you're showing, right? Your units. If you follow your units, you'll avoid a lot of your mistakes. So that's what I'm saying. So if you want to look at anything, you want to try a different assumption or anything like that, you know, anybody? Okay. So that's residential, right? It's kind of on the small scale things. So let's go back to the presentation now. Oh, you closed it? Oh, I forgot to keep going back and forth like that. All right. There? All right. So, all right. So we'll go to the, yeah. Oh yeah, we're going back and forth. We're gonna go back and forth. So okay, so here we are, residential. So now we're on commercial. So in commercial, okay, defined as a business. So that's retail, restaurant, pubs, services, and small scale industrial. So all your little shops, little fabrication shops and stuff like that. It's because they're deemed more commercial and then they are really industrial. So again, the main consumer here is natural gas. This is mainly served for building heating. There's a small usage of RPPs for different things, but most of it is heating, but there's a little more involved. So I've changed my coefficient of my energy efficiency gains. Instead of 2.5, I made it 2, right? This time around. So then when you look at it, then we go to commercial. So again, we start off as a total use. We had 360 terawatt hours. Electricity was 64. And then, so natural gas didn't change. Yes, it did. All right, we're good. So that was the energy start. And then we come along. And then as I'm converting things around, right, I end up, so my net usage now is 820 megawatts. So I'm assuming my efficiency, where'd it go? The 80%, my 80% efficiency on this side to get these numbers, and then our 60% efficiency. Sorry, and then the 2%, the factor of 2 electrical efficiency by electrification. So now we're at 820 megawatts, right? So that's our number. So again, if we want to challenge these numbers or change them and see what happens, right? We can, right? Well, if not, I'm not going to switch around. If we're not going to challenge them right away, can always play with it later. So then you go to the next one. Why is it not switching now? Okay, now industrial. I'm leaving transport to last because that's the one everyone wants to talk about. So we'll go industrial next. So industrial one. Now this is the big boys. These are all the big users in the province. So like I said, pulp mills, mining, sawmills, any larger factories down the Lower Mainland or anywhere else, right? That sort of stuff. These are the big units. So these tend to operate 24/7 or something close to that. So therefore, the assumption is going to be a little different. But in this case, like going, okay, so their fossil fuel energy they're used is a mix of all kinds of fuels, right? So fossil fuel energy. But I'm assuming in all cases we're getting a 60% thermal efficiency on their usage, right? My first guess, right? Is like, what can we do? And this time, when you convert it, there are no electrical benefits converting. Is whatever energy you got here is the electrical energy equivalent you're going to have to produce to have in the industrial process, right? So there's no savings there. So when we go, okay, so now, we go. So there we go. So so now we look at everything. So the net usage per year, as you can see, is quite a bit higher, right? And the net result of that, so like I said, my efficiencies for the process is 60%, but my efficiency for the refined products is 30%, because like I said, most of those are going to be like your stationary machines that are diesel operated, or your short site working machinery like your loaders and whatever that moves around the yard, but they don't go on the road, so therefore they're not treating transport. So that's their diesel operated. So I'm assuming those are 30%, because we're breaking down. So the refined products is then I'm showing that as a 30% efficiency, while everything else is at 60%. So when you factor all that in together, guess what? Look at this one. 5,370 megawatts of generator capacity is required, right? Huge, right? Just so we can move ourselves off fossil fuels to produce things in this province. So again, anybody want to change the assumptions or anything like that and see and play with the spreadsheets right now? Somewhat. Because there's more energy in the fuel, but the thermal efficiency is not much better. Oh, okay. So the question was, is diesel more efficient than gasoline, right? And the simple answer is relatively no. Kind of, sort of, but no, because it has to do with the thermal efficiency of a heat engine, right? It doesn't matter if it's a diesel or a gas turbine. You're looking at the thermal efficiency of a gas engine. And the thermal efficiencies in most gas engines will run between 25 and 40%. The 40% ones generally are these huge industrial gas turbines, the ones that do for power generation and stuff like that. They're like 300 megawatts or 600 megawatts, and they're the size of a small, bigger than a house, right? So huge things, right? So because you just have so much energy needed to compress the air, so much energy going through the walls into the environment, and so much energy that is not used to do the final work that just goes out the stack, right? So you can barely get 40%. So I've made my assumption on those to be 30%. I'm being very generous. But if you go higher, it just means that more of that energy, of the net energy, is more. So therefore you need more electricity in order to replace it, as opposed to less, right? Because the less efficient you get, the less energy in the end you're actually doing work with, right? But the point is, and I bring it up now only because it's one of the things we should, as a really red flag, saying that if we're moving into things like LEDs and everything, trying to improve our efficiency, why are we sticking with efficiencies of machinery and moving and transport and all this that are 30%, right? So 70% of our energy is just going into the air or up the stack, right? So it doesn't, you know, in the terms of modern age, does it really make sense anymore, right? So this is the big ones, 5,370 megawatts of equivalent power to make it work, right? Go to the next one then. Oh, you got that working. All right, so now the fun one, transport. This one, we break it down into the various fuels, right? It's not, I'm just not breaking it up. I break it down into various fuels. So the fuels we have, liquid propane, biofuels, which is green diesel, diesel, in their case, low sulfur, gasoline, aviation fuels, which is basically the mix of all of them, avgas and all of JPs and your kerosenes and all that sort of stuff, which is mainly a very just a lighter derivative of diesel, really, and really to think about it. Heavy fuel oils is like submarine distillate and bunker Cs. In some cases, there are some using lubricants or burning lubricants, or diluting them and then burning them. I don't know exactly where, but apparently the data showed lubricants being used for transport. So I'm not sure where. And then obviously hydrogen, right? So basically, as I go on, as I described, it's basically these are all heat engines driving it. So therefore, heat engines are assumption of 30%. And then again, once energy is derived, once the net energy consumed to actually move you is derived, there are no electrical benefits. There's no efficiencies going electric. And I did not factor in your charging efficiencies and your standby efficiencies on a battery electric and stuff like that. Because it's wrong, you're getting around 95% really. So you know what? For now, I'll leave that out, right? Because, yeah, question? In that there, so where I had home heating, so when you go, so no benefits going electric when it comes to transport. So look, if you go back to home heating, I said when you go switching from a gas furnace to a heat pump, the heat pump has significant better has an electrical efficiency over what a gas would. Where gas, you burn it, you get heat. Where electric, where you put for every, depending on the COP, the coefficient of productivity, for every unit of energy you put in, you'll get 2, 3, 4, 5 units of energy out, right? So there's an efficiency there. So it's not a 1-to-1, unless you do resistive heating, and then you're back to 1-to-1. So in this case here, once you figure out your net energy that needed to move you from A to B, going to a battery, it's still the same amount of energy that you need to move from A to B. It doesn't change, right? You can argue it can change a little bit because the vehicles are heavier or lighter, all that. But again, this is a first level cut, trying to get a high level, get the big picture. Oh, it is, but so if we go to the next slide, it'll make sense. So
Beginning of the presentation that you missed as well.
I'll cover this in a second when we get to the numbers. It'll make sense when we get to the numbers. So some of the things I had to assume. So I said biofuel is renewable diesel, is right. Aviation fuels, I'm just assuming kerosene, so I don't I assume they're all for one thing. Heavy fuel oils, and I'm just stating that as a conventional diesel. And lubricants there's a thing called residual oil in terms of the energy content. The energy content I was taking from there's the engineering toolbox in the website. There's a website called Engineers Toolbox. And in there they have a table that says, engineers for assumptions. Here's the energy content of all these different fuels, right? So I'm using residual oil for the energy content. And then motor gasoline is I'm saying reformulated low sulfur gasoline. That's pretty what we have now. So next slide then. So we go to the numbers. So now the numbers. So you can see is that for electricity, so all the electric vehicles are out there now, in 2023, there was 0.61 terawatt hours a year consumed electricity, right? Just to give you an idea. Compare that to propane, which is 0.85, natural gas, only 0.1, biofuels, almost 10, right? Hydrogen's very little. Aviation fuels, quite a bit. Diesel, look at this one, it's 27, it's a big number, right? You can expect that, it'd be a big number of net raw usage of energy. Heavy fuel oils, but then the other one, look at gasoline's 40 terawatt hours of raw energy, right? Raw energy. So this is if you had a liter of fuel, I have this much energy, I have X number of energy, right? In that fuel. So now, so when you factor in what I'm using, so assuming a 30% efficiency, right? So if you look at it, one thing I want to bring out, so let's look at the volume. So diesel, find my diesel again. Diesel, low sulfur. 2,700 million cubic meters, or 2.7 billion million liters of diesel fuel for transport. And if you went back, I didn't point it out, in industrial, it was 2.5, right? So the total sum is up in the 5 range, right? So 5 billion liters of diesel fuel a year is being used in this province. And then I come down to motor gasolines, and I'm at 4.6 billion liters of gasoline used in this province in 2023, right? Just to give you the scale of things. So it's big, right? So when I factor all that in, so the net usage after 30% efficiency, you can see where I'm at, right? Is so where we started off at 40, we're down to 12 on the gasoline. So basically from moving, so every car that has running on gasoline to go to A and B, you needed this much energy to go from A to B. There's your electrical efficiency coming in now. So an electrical would need to use this much energy again to move the same distance, right? I'm not, like I said, I'm not factoring in slightly efficiency here or disefficiency there, because some cars get better mileage than others, and so this is for a very high level, remember? So when you factor all that in, so what I'm doing is, so the red ones are indicating ones that I'm not included in the total generating capacity that we're looking to calculate. So I'm not calculating in aviation fuels because the technology is not there to go electric in the near term. And I'm not factoring, and biofuels, as I've said, my original one, all biofuels are already neutral for us. So we'll continue using biofuels even if so it's not really something we'll replace with electricity. So the net result of that, when I take all these numbers and do the conversions, is I'm at 2,448 megawatts of electrical generating capacity required for transport fuels. So that's the megawatt you needed to generate this much terawatt hours of power in a year, right? So if you're doing the math in your head, right, these numbers starting to get big, right? So now I'm going, well, let's summarize this. So I said, well, residential, unrounding it, there's 740, commercial 820, industrial 5,400, transportation 2,450, right? Put it all together. So when you tag it all in, fossil fuels and was basically producing, you would need 82 terawatt hours a year to replace all fossil fuels, right? 82. I bring this up because this was the usage of electricity in BC at the same year, right? A lot more electricity. So then this number then converts, when you sum it all up, to 9,376.33. Engineering me had to leave a couple of decimal places in there, of generating capacity, megawatts of generating capacity, right? So then well, what does it look like? So what does the existing grid look like? Well, there's hydro off grid, best information I can find. There's about 5,500. That's all the private stuff, like your Kitimat smelter, which has its own power generating. They may sell some on the grid, but most of it's used to run the plant, run the smelter, right? So that's not on the grid. There's a few others like that. There's a few more down in the Columbia region. So therefore, they're not on the grid. So hence red, I didn't count it as a total. So BC Hydro has about 10,400 megawatts of generators built into their dams everywhere in the province. Biomass is around 925 megawatts. Wind is sitting around 702. Natural gas Power generation, 440 megawatts. And petroleum, about 18 megawatts. So it's not very much, right? Because so, and then solar is sitting around 15 right now. So when you look at that, so the total grid, excluding the red, 12,485. So that's what we have now. But the usage factor is only about 53%, right? So the equivalent, so in order to produce 64 terawatt hours a year, worked out to only 6,600 megawatts of generating capacity on an average day online. And the reason for that is that hydro is the big killer. So when you look at Site C forecasts, you look at Peace Canyon, you look at most of the ones in the Columbia River, you're seeing usage factors around 53 to 55% throughout the year. And that has to do with the water changing levels, has to do with taking outages. You know, you got to take a dam off. I got to take a power unit offline because you got to cycle the sluice gates and everything for maintenance, and you got to check the bearings and all that. So you lose about 60 hours there at least, right? And then the water being high and low and controlling it, the result is hydro is only producing, the last time was 53% of your installed power is what's actually producing electricity at any one time, right? It's a little more in the high flow season, a little less in the summer, but on an average day, 53%. So that the result of that is 6,600 megawatts will get you 82 terawatt hours a year of power, right? So that's 64 terawatt hours of power a year. That's what we are sitting at currently. So then I go, okay, so now we know that we need to generate 82 terawatt hours a year, or 9,400 megawatts installed on an average day, right? And producing, right? So what does it look like? So I made the assumption that I'm going to say, let's say I'm just going to go, let's do it all in solar, and then, or let's do it all in wind, let's do it all in nuclear. And I did not factor in hydro dams because we're pretty well, like I said, the water efficiency and everything is low. And I think that we're pretty well reached the limit of large scale dams that we added in this province. You can probably stick in some run of the river stuff, but it's in 10 to 40 megawatt range when we're looking at 9,000. So I said, you know what, that's in the rounding error for what I've been doing at the scale I'm doing right now. So I said, well, let's look at wind. So solar, wind, and nuclear, right? So starting off, let's go solar. So I assume, I assume that 82 terawatt hours a year being replaced with solar. I'm assuming a power rating of a panel at 300 kilowatts per panel. The energy output of the panel, 104 kilowatt hours per kilowatts of power of rated panel per year. And I got this from the BC Energy Hub. They've done some studies. They've done it for every province. So this was their study. And I talked to Doug about this, or emailed Doug about this, and he had his panel, and he told me what he generated in his first year. And for Prince George, different parts of the province is different numbers. For Prince George, it was 1050, right? So when I use that, and they're rounding around too. So when I used 1050, it was pretty close to what he was able to generate in his first year, right? He was a little shy, right? And then they said, okay, well, you don't know where these things are going, right? So therefore, we're going to spread them around the province. So because it's spread around the province, they did declare an average for the whole province. So we'll just use, so that's the number I'm using. So then I said, well, okay, you need every panel, but not every panel could be producing at all one time. You got some down for maintenance or some, whatever's going on, right? So I said, well, I'm assuming then that we have a 25% that we need to add to the total in order to have enough solar panels to meet my 82 terawatt hours a year, right? So when you look at the net, so basically, I said, before you apply this redundancy factor, 272,754 panels are required to be installed in order to produce 82.15 megawatts, terawatt hours a year. Add the fact, multiply by the redundancy factor, we're at 304, I'll say 41,000 panels at 300 kilowatt panels are needed in this province, right? So the question is, do we have enough room, real estate, to be able to put this many panels in, right? So you think about it, you go 10 per building, well, you need 34,000 buildings in order to do it, right? So it's like if you want to do it that way, right? Which is probably doable. I don't know. So again, so that's where I'm at. So I don't know if you guys, want to, we can change this number if we want, whatever. I have to see my spreadsheet. We can play with it. But that's so that's the redundancy number. So that's wind, or that's solar, I mean. So that's what solar looks like. So now let's look at wind. Agricultural land reserve. So let's look at wind. So wind, I'm saying, okay, I need to replace 9,400 megawatts, right? So I looked it up, and the current technologies that are in production and in put in service right now as a higher power for onshore only, onshore generators only. Believe it or not, there's GE's making as GE Cypress a 6 megawatt unit, right? So okay, I'm going with 6 megawatts. But just how much power does a wind turbine actually produce in a year? Well, I looked it up, and then the best I could find was 41% of your rated power, right? So of your 6 megawatts, on an average in a year, 41% of it is actually producing electricity. And I got that from the USGS, just looking at their data and everything. So therefore, it's basically, if I'm looking at that rate, so then I go at 6 megawatts at this power factor, you're going to need 3,800 of these puppies in order to produce 9,400 megawatts equivalent of power, right? So then I said, well, again, I'm sticking with my 25% redundancy factor. So we're at 4764. So these are big puppies, right? So then where are you going to put 4,700 wind turbines in this province? It's a good question, right? Yes, Doug.
Yeah, how many wind turbines we currently have?
I forgot to look that up. I said that, so I think we're only sitting around 100 or so, 140, right? Yeah, so you can see the scale we're looking at, right?
A long ways away.
We're a long ways away. So again, and I didn't really I didn't do the math to factor in offshore, because offshore you can get these. I got 10 to 15 as a viable. At 15, but they're offshore now. They're proposing some up to 20 megawatts each, right? The problem with BC is the West Coast is a lot of rocks, very narrow, and it goes deep real quick, right? Because it's an induction zone, subduction zone in the planet tectonic plates. So there's no real location other than maybe around the Queen Charlotte Islands that you can install. So I didn't figure that offshore is really a viable solution for us to be replacing everything. So if you want to go wind turbines, you're pretty well going to be sticking them everywhere, and everyone's going to getting used to being Dutch, right? So that you can get used to seeing blades rotating all the time. So that was wind, right? Or Danish, yeah. So then, so let's go nuclear. So nuclear, I said, well, let's go. Well, I did both. So I'm going, that's assuming a new version of a modular reactor, which are around 300 megawatts each, right? So, and then I also said, well, a CANDU reactor is also about 820. So if you look at the Ontario generating plants like Bruce Nuclear or Darlington, they're about 820 megawatts each, right? So, and then I'm assuming 80% average usage, and that's based on Bruce Nuclear. Their own nuclear power plants are running around 80% of actual usage capacity on average. So I'm following the same one as them. I initially thought 90%. Basically 90% of the time the reactor is producing 90% of its available power, right? So if you took 300 times 8760, that's the total megawatt hours you'd be able to produce, right? But you don't run all the time. And so I'm assuming 80% for now. And then I'm only assuming 8,700. I'm leaving 60 hours a year for maintenance purposes. You shut the machine, you shut the reactor down for 60 hours, up to 60 hours, do maintenance. So So basically what it works out to is each modular reactor can produce, don't forget the CANDU, I forgot to update that number. So the CANDU, for that one there, it's 2.35 terawatt hours a year per modular reactor. That's what it can put out. That's what you can reasonably expect to put out per reactor. So when you do the math, that means we need 39 of these puppies spread around the province, right? Because they all need cooling water and all that sort of stuff. So they are, so you need 39 of those. However, reactors are not always online. So I'm assuming a 5% outage requirement on those reactors. So when you turn around and fix that, that means in order to make sure you're always covered, you need 41 of these reactors installed somewhere. So because at any one time, 39 of them have to be running. So that's where I got my assumption. Very interesting stuff. And then if I use the CANDU reactors at 820 megawatts, it actually works out to about, this 41 turns into 15, right? But that's so, and if you think about it, 15 is the same, roughly a little bit less than what the Bruce nuclear power plant is 6,550 megawatts using 8 reactors. So you basically need 2 of these Bruce nuclear power plants. Go look it up what the Bruce nuclear power plant looks like, right? So you would need 2 of these plants with probably 7 reactors or 7 or 8 reactors each, right? And then you got to be located in places where, in a seismically safe location. All the nuclear needs to be pretty well and seismically safe. You don't want to do the Fukushima happening all over again, right? So you want to put them in places inland where it's less likely to be affected by earthquakes. But they also, when they go inland, they also need a good water supply, because part of the issue with nuclear is you're back into the steam cycle or Rankine cycle. So therefore, you need cooling water and the sort of stuff so that you can run your steam cycle, right? So the steam cycle is you heat it up, create steam, you expand the steam in a turbine, steam comes out the other end at a low pressure, but it's still steam because you can't let it go to water because it'll destroy the turbine in the process, because the turbine's made for gas, not for liquids. There's some that do both, but yeah, but generally for efficiency purposes. And then you get the steam, then you got to run a bunch of cooling water through it. So you can condense the steam back into water so that you can feed it back into the turbine, into the heat cycle again, so you can regenerate steam. Well, that generally is around the best plants, like even like going back to boilers, is about 65% thermal efficiency, right? Now you can improve that if you want to go combined cycle. So combined cycle is you would take some of that waste heat, but instead of condensing it right away, is you would feed it into a district heating. So into a community, if you got a community nearby, you'd feed it into district heating and community, you'd feed it into an industrial process. And that means you would then have less energy come back that you need to reduce to get the steam. So, as the steam plant guys call it, it's a low pressure steam. You put your low pressure steam system into play and make use of it. So there's a good idea of what's going on with nuclear, right? So just to give you a scale of things. So in conclusion, so in 2023, I estimated that we needed 82 terawatt hours a year of electrical energy generated to replace all fossil fuels. That works. So if you look at it, that's 127% of the electrical usage of that same year, right? So basically we need to more than double the generating capacity of energy, and not just energy now, that we have currently available, that's currently producing, right? So, or if we look at the generating capacity, so that is either 70, so the total, as I showed, the total energy available, total power available of installed power is 12,400 megawatts. So of that, we need 75% of it installed. However, when you look at the usage it's only 6,600. When you look at the use, so therefore now of the available, we're at we need 142% of installed capacity currently in order to produce the same amount of energy. Just to give you this idea. So look at, and believe it or not, these are very similar to what I had 10 years ago, or back in 2010 when I did it. So it hasn't changed, right? And you can see that based on the first slide I showed with the total energy, that year after year after year, the total amount of energy really hasn't changed in this province, even though the population is going up, but there are efficiencies in the usage. So there's a bit of a balance, right? So like I said, For 2023, 64 terawatt hours a year was consumed in this province, of which 11.2 was imported, mostly from Alberta. Like I said, 6,600 was the equivalent generating usage of energy, of power, I mean. And then obviously, and like I said, the obviously is we're not going to do all wind, all solar, and all. It's going to be some sort of mix. What that mix looked like, I have no idea. Right? That's into the politics now and into the engineering and all kinds of other factors in there. I leave that to you to imagine what that mix is going to be. And I didn't bring up, and there's all kinds of others. You can throw in some run of the river, you can throw in some wave power, you can tidal powers if you wanted, you can figure things out like that. But the point is, we need to get there. We need to get to 8,100 terawatt hour, 81 terawatt hours a year. And that's just, life hasn't changed. Like, no, life is going to change, but if you assume life has, that's where we're looking at. So, and that's to me, based on my son, that's a low number, right? So I purposely made a low number so that as things get better and life's changing, you're not going to necessarily go to a high number. You're going to be closer to the lower number range anyways, right? And so, and as you do an incremental building over the years, like this number will have changed as things, as new technologies come online and all sort of stuff. But the whole idea is, my point is, you now have an idea how big the elephant is, right? And you have somewhat of an idea. It's just what has to happen in order to eat that elephant, right? So, and then, and like I said, this is a high-level estimate as a first kickoff point. As I jokingly point, this is like an engineer on the back of a napkin type calculation as I've done. But I started with real numbers of energy consumed as reported by the government, right? So, and that is the end of it. So I'm up for any questions, comments, rude remarks, anything like that. So we'll go from there. So first question.
I'm curious, did you calculate what it would cost to put in all the solar, put in all the wind?
No, I did not.
Because
I started looking at that.
I think solar will be the cheapest, then wind not too far more expensive, and nuclear multiples more expensive.
Correct. Yeah, I didn't get, because I was looking at wind and I was seeing numbers in such a wide range. I go, what do you believe, right? So I'm going, I purposely left that out of the presentation because the data is so far varied that your opinion is as good as mine on this one, really, when you look at the data. So, excuse me. So there's no need to be bringing it up here. That's why I left it at that. But yeah, you're pretty well right. I think solar is going to be the cheapest to install. Wind will be next. And then nuclear is the most expensive. However, nuclear is more stable. It's 24/7, right? One of the advantage BC has, because with our water levels falling, our water availability, is you could go things like wind and solar, build more of it than what I've said, use less of the dam, leave the dam for background, and let them set the pace for the baseline of the grid. Everything feeds onto that and matches that for your power and your syncing of your frequencies and your cycles and all that. And let the dams be the variable load machines as required to cover your cycles as your solar goes up and down in a day, or as your wind goes up and down through the day as well, right? So you let your dam take advantage of that, let that carry on that way. But I don't know if that's a feasible approach for dams to be cycling their loads that much. I don't know. That's a lot of mass spinning around that you aren't.
Solar, water. See, solar, you're going to need storage with water on top of the hill or batteries of some kind of chemical nature.
Yep.
So that adds to the cost potentially, because hydro's got to maintain minimum water flows.
They do. So, and they have, and in some cases they have maximum too, so they don't go washing things out. So
yeah. So it's not an easy question.
No,
I did the transportation stuff, and very close numbers, subtly different efficiencies, etc. But
yeah, like I said,
just gasoline, you need 3 Site Cs or something.
Yeah, well, like Site C is what, 1,100 megawatts, but at 53% is 5,400 gigawatt hours, right? That's it, and that it works out to about 54%, I think, of the installed power, right? What you do the math? It's so 1,100 times 8,700 by 54. it's down around in the low 50 range. So yeah. So it helps, but it, you know, 'cause everyone going, oh, well, we're putting in 1,000 or 1,100 megawatts. Yeah, but you're not getting equivalent of 1,100 megawatts equivalent of energy generation out of that, right? So there's some,
Theoretically, you can ramp up and ramp down the hydro power generation fairly quickly. But I have heard that the more the water level fluctuates behind a dam, the more different environmental implications, including greenhouse gas emissions, occur. So the fluctuation isn't necessarily what you want either.
so, and I bring that up because with the energy, because remember, 2003 was 64 terawatt hours per year of energy consumed. And as I previously said, 11.2 of that was imported because hydro could not make up the difference. And if I went back to the other one, you would see the hydro was a very constant 54 to 58 terawatt hours a year, right? And for some reason this year it could not even make that. So therefore you need to import even more, right? So
Can I make some comments?
As they can buy power cheap from Alberta or
True enough.
Washington. I
True
don't know
enough.
how much of the 11, but they play that game.
and low demand, they'll buy power because the price drops. They're playing the spot market as opposed to playing contract prices.
So steamers, big guys, they want to go steady state. So
Correct.
they'll sell power cheap.
So
And we have about 10 years of drought, which is making them more cautious about generating. Online, Doug?
Yeah, two things since you're on that topic right now. Yeah, I'm not sure I agree with all the comments around the feasibility of using hydro dams as batteries, basically. There's obviously a lot of complications, but a lot of what hydro does, as I understand it, is, I think you just mentioned it, is they buy power when it's the cheapest from, say, solar in California in the summer, in order to hold back on generating from their hydro facilities, and then they ramp up their hydro facilities when they can sell it to the Americans for a profit. So it's not just strictly a case of, oh, they didn't have enough water to generate the power we wanted. They made
Fair enough.
they made a deliberate thing to say, well, let's conserve a buffer in our hydro dams and take advantage of the price differential. So it's not quite as simple as you hear in the media of, oh, they ran out of water. Anyways, what was my other point? Now all that might change with all this political stuff going on right now. Anyway, the other thing I was just going to mention, more of a point to mention, is I just came across a while back, interesting little study. Well, not so little, a study done by, was commissioned by Natural Resources Canada, and they estimated for across Canada, but they broke it down by province, the the potential for rooftop solar. And of course, they had to make a lot of simplifying assumptions. They took 11 municipalities and they actually mapped out rooftops using LiDAR, and then looked at, solar radiation statistics from Environment Canada and so forth. Anyway, long and short of it is, for BC, they estimated 41 gigawatts of potential rooftop solar. And they say that's probably on the high end because they didn't take into account some other things, like maybe some buildings aren't structurally able to hold it or something like that. So anyway, so that's probably the max. But
and you're
I
talking
thought,
41 gigawatt hours, right? Not gigawatts.
no, 41 gigawatts of generation capacity. It was just a second here. Let me look. I got it open here. Hang on.
Well, that's way more than we ever need.
Well, let me double check that. If you just give me
It is
half a
what
second.
pet peeve when people confuse gigawatts and gigawatt hours, and they mean two
Yeah, it
different
said so.
things.
It said so for
So-
BC. Can you hear me all right? Yeah. So for
Yeah.
BC, it said PV photovoltaic capacity of 41 gigawatts.
Okay.
PV electricity, so actual energy generation of 30 terawatt hours.
There you go. Yeah.
I mean, I saw, like I say, I'm sure that's like an upper limit. So, but it really struck me as, wow, that's quite a bit. Anyway, that's all I just wanted to mention. If you, if
Hey.
you're interested in that study, if you just quickly Google Natural Resources Canada rooftop solar potential, you'll find it.
Okay, thanks. More data, the better, right? That's the way I look at it.
So that electricity that's been imported, is that accounted for the electricity that's been exported as well? In the total?
So that 11.2 is a net import. So if we exported, the net is 11.2 in, not total. You know, as you said, some's exporting and then they buy it cheaper later. But but this year, that year, they needed to import a net of 11.2.
Water was bad.
Low water was a factor. So, and I said 11.2 over 64, 50, you know, roughly 14%, right? So
Anybody else online?
I'll just make one more little closing comment if I can.
Go for it.
Yeah, I was struggling to follow all your numbers the whole way through, but they do sound, you know, like not too far off other reports and stuff like that. So as you say, you're trying to get just a, you know, a rough you know, a scope of the problem sort of thing. And so I think you did a good job there. But anyways, the the way I see it is it's a big challenge. Big challenge. Of course, we're not going to do it overnight, but
Nope.
it's a big challenge, and but it's not entirely beyond the pale either. That's sort of my take home.
I agree. It's doable. It's just a matter of it will and getting the business environment right so it's like the economics are there for it to happen. So
And we're going to have to accept that there's no way you can have a modern lifestyle without impact on the environment. So all these things, wind, solar, um, nuclear, any of those methodologies you're talking about, they all have negative impacts on things. So,
Yep.
You know, it's a case of do the least harm is the way I think of it.
correct. Every technology has some downsides that you have to trade off and figure out which is the trade-offs we want to accept and not accept in order to decide the technology you want to go forward with, or the mix of technologies you want to go forward with. Yeah. That's what the engineers of the world are for, right? And to help you figure that out. So yeah, so it's like I said, you know, the whole point of this was, like I said, is people going around with their wags, their wild ass guesses, and I'm just trying to get you numbers to get you down inside the ballpark now. So this is what it kind of looks like, a snapshot in time based on 2023 and a whole bunch of rough assumptions. So now you should give an idea that you're in the ballpark. So what it actually looks like in the end, like I said, is different. It's definitely going to be different, but this at least gives you the idea of the scale. So, because most people don't appreciate the scale. Like when we did with the politicians there for the election, right? They don't really appreciate what this scale is. I don't know what they're dealing with. They're not knowing. They don't know. They didn't appreciate what the scale was, right? So they go, oh, we'll just do this, and you hear them even talking. Well, we just do this. We just do a little bit of this. Do a little. I go, you're still just putting cup of water inside of a pool here. So you probably need to go think a little bigger scale. So, but anyways, that's so I'm hoping everybody has a better appreciation of what the numbers look like. Like I said, I leave it to your own opinions on the scale of it, and you know, my assumptions to go up or down or whatever that stuff. So to make the numbers change a little bit, but you know, because someone else do the same thing, and or another engineer likes to go to third decimal places, we'll go a little further and refine it even more, right? So, and I was trying to keep things to the nearest integer. So it's like just start, you know, rounding up, rounding down type stuff. So because the assumption is just so rounded, so many other things that it's in the air. So
I was just wondering if anybody knows about the nuclear potential. Are there other Western provinces? Does anybody have a nuclear plant of any size?
so all the plants currently in Canada are Ontario and New Brunswick, right? Mostly in Ontario, and there's one plant in New Brunswick. Although Manitoba is looking to, because they're a uranium hub, they're trying to expand that business. So they're looking at doing uranium refining and then maybe allowing some of these modular nuclear reactors into their province as well. Because if they're producing uranium and refining it, well, let's put in our own reactors as well, right? So, and then the Western United States, they were looking at a few. There was a project a while back, last year, that we're looking to do one company was looking to build a demonstration plant. And then because of the market changes and the price spikes, they found that it was no longer economical to build. So they've shut it down. Now it's going to be it's a northwest state somewhere. Like I can't remember if it was Montana or Idaho. It wasn't Washington though, but it was up in that area of the woods, right? So that was, they were looking to do that. So there's still some companies looking to try and get a 300 megawatt modular up and running. There's many companies in Canada looking at it, and then you've got a Canadian Nuclear Authority who are sponsoring some of them to try and get something built, so they can be a leader in this as well. So we'll see. Yeah. Well, you look at Ontario. 50% of the electrical generation in that, or consumption in that province, is actually generated by nuclear. 50, and that's 10 to 11 million people. So, like Quebec's obviously they're hydro everywhere, but yeah, so it's, and that's just two plants. So one very large plant, one smaller one. And Darlington, they're even right now, they're construction. I forgot to mention that. They started with building one 300 megawatt modular unit. And then they're having lots of success with that. What they deem success for nuclear. And they've said they've opened the project to go 6 or 8. Can't remember now off the top of my head. Darlington Nuclear Power Station. It's about an hour east of Toronto. It's on Lake Ontario. So because their CANDU reactors are in the 70s vintage. They've already been refitted once. So what can we do to replace it? So they're starting to look at building these modular ones as a replacement. How successful they'll be, we'll see, right? And then modular, you're going different. You can either have your pressure waters, the molten salts. Now the new types of reactors, they're going into the new technology as well, because most nuclear power today is pressure water, right? So, which is the problem. Whereas opposed to a molten salt, its natural state is to be offline, and you don't need power to shut it off. Like they literally, as someone pointed out, is you have the thing running at high temperature at low pressure, and you run water through it to heat the water up, and then you run that to a heat exchanger to create steam, or you run a fluid through it to heat. And then the bottom of that vessel where the nuclear is happening, there's a small drain with a fan blowing across the drain pipe, and the fan's cooling it, creating the molten salt, solidifies into a plug, and it just holds it all up there. And then if the power goes off, the fan shuts down, the plug heats up, melts, and everything drains out and shuts the reactor off. Just its natural state is to be off, not on, right? As opposed to pressure water, you need to have all these cooling water pumps running all the time. So you have backup generators, which is Fukushima's problem. The generators are close to the water. The tidal wave came in, knocked all the generators off. It screwed up the control. So the reactors went haywire. They couldn't shut them down because they couldn't keep the cooling water going. So blah, blah, blah. So hence, so reactor technology is changing as well. So it's interesting things. Modular is looking to try and take advantage of this, as opposed to doing large scale, like a CANDU size reactor or Westinghouse size reactors that are out there right now.
The question?
Not a question, just a comment that, if you aren't wasting enough time already looking at your phone, I've got a great app for you. It's called the electricity map.
Oh yeah.
And it shows the whole world. And you just click on a country and it shows the breakdown of energy sources. And it shows which direction the energy is flowing to other countries and whatnot. It's so you mentioned France there, and I thought, oh yeah, I'll just check on France. And there's the purple line there is nuclear in France. Yeah, Finland has more nuclear than hydro. And
No.
so
Yeah.
Anyway, like I said, if you aren't wasting enough time already, electricity maps. Yeah, it's good fun. Our son lives in Netherlands. He sent a screenshot of it.
Oh, yeah.
Shows the usage from different sources throughout the day as well. Using solar.
Yep, yeah.
and,
There's a lot of data out there. You just spend the time mining it and it's like. Well, like I said, like I started off with Canadian Energy Regulator, data. And their data is basically reported to whatever, they basically take whatever the carbon taxes are and the generator reporting from the utility companies. And from that, do their estimates of how much energy is actually being used in a year, right? And they report as like I said, in petajoules. So 10 to the 16. It's like, so, it's quite a big number. So.
You really gotta watch the units, which is what you started out telling us about.
Yep.
And also the powers of 10, because you can go to StatsCan, gee, looks like 5 million liters for BC. Gas, like, that doesn't make sense. Tiny, tiny print times 1,000.
Yes. Yeah.
You
Yeah.
gotta watch stuff like that.
Yeah. I guess I go back to my old high school teachers. You always watch your units, otherwise you get yourself in trouble. So to this day, I still remember that. So
Well, thank you very much, Gil. Appreciate
I hope
your-
everybody found it interesting and somewhat informative and to help you better understand what the big picture is, and we'll go from there.
Yeah, I appreciate you going to real life numbers and working from there and the transparency with your assumptions. Excellent. Thank you.
You're welcome.
Thank you.
All right. Anybody want to come up and play with a spreadsheet? What? Sacrilege. Absolute sacrilege. I got them saved up.